Right, so linearization and differentials are two very simple applications of the derivative. They're basically two simple techniques that allow you to compute complicated calculations without the need of a calculator. They are really similar and both of them involve a common formula, but you're often expected to know the slight difference between them, so we'll start off with linearization and then get on to differentials. So if you have any f of x and you're asked to approximate it or solve it by linearization, you use the following formula: f of a plus f prime of a times x minus a. The only difficulty really in these questions is deciding what to set as your a. A must fill in two criteria. First of all, it must be close to the given x. So the given value of x that you're trying to compute must be close to a. And secondly, your a must be a value whose exact answer you know when plugged into f of x. I know it sounds confusing, but it'll get simple once we get into an example, which we have right here. So let f of x is equal to the cube root of x. Approximate the cube root of 1.03. Now our first step always is to set our a's. So for our a, it must be close to 1.03, and when we plug that a into our function, we need an exact value. 1 seems close to 1.03, and well, if we plug 1 in here, we'd get an exact value of 1. So let's set a equals to 1. X is our given, which is 1.03, and that is literally half the work we had to do. Now we've got our formula right there, and we plug in. So f of x is equal to f at a, which we set as 1, plus f prime at a, multiplied by x, which is 1.03, the given value, minus a, which we had as 1. All that's left to do really is to find a formula for the derivative. We'll do that to the side right here. So if f of x is equal to the cube root of x, to find its derivative, we'll first convert it to a power function just to simplify it. And then for f prime of x, it should be pretty straightforward. We bring our power down, subtract it by 1. So 1 over 3x, well, to the power of 1 over 3 minus 1 would leave us with 1 over 3 x to the power of 2 over 3. I did skip a couple steps there, but this should be straightforward, really. So if we go ahead with our formula now, f at 1, we know when x is equal to 1, we'll get 1, plus f prime at 1. So if we plug 1 into this f prime here, we'll get 1 over 3 times 1 to the power, which becomes insignificant since the base is 1. So we're left with 1 over 3. And then x minus a would leave us with 0.03. Then we have 1 plus 0.03 divided by 3. To get this into one fraction, we do simple addition, which would leave us with 3.03 divided by 3. Now with linearization and differentials, you must always remember that you're asked to find a final answer in terms of decimals. So we'll go back to 6th grade or 7th grade, whatever it was now. Take the numerator inside the house and divide by the denominator. 3 goes into 3 once. Remainder is 0. Put the decimal where it belongs. Get the next number down. 3 goes into 0 0 times. Get the next number down. 3 goes into 3 once, and we have a remainder of 0. So the approximate value of the cube root of 1.03 is equal to 1.01. Pretty neat. So that was a straightforward example really on linearization. We'll get on to a differentials question now. So again, we have another formula, obviously very similar. In fact, if you think about it, it's nearly identical, except for this part right here, which we'll go over a fair bit in this last question I have. So if you have any f of x, the formula would be f at a again plus f prime at a again times delta x, which will be f at a minus x. This is just a formality, really. It's written this way in differentials. So another example, use differentials to approximate the square root of 9.1. So if you notice, you're not given an f of x here, but it is pretty obvious. If you have the square root of 9.1, you'd expect your function to be the square root of f of x. So let's just let f of x equal square root of x. Now, on to our a first. So a needs to be a number close to 9.1, and if we plug that into our f of x, we get an exact value. Any ideas? I wish I could hear you guys through this camera, but I'd expect most of you to be going for 9. Pretty close to 9.1. And if I have the square root of 9, I know that's exactly 3. So let's let a equal to 9. X is our given value, which is 9.1. And that's it. We're on to our formula now. So f at a plus delta x, 9 plus 9.1, is equal to f at a, f at 9, plus f prime at 9, times delta x. F at 9 we know is equal to 3. F prime at 9 we still have to compute that, so let's do the derivative right here. So if f of x is equal to the square root of x, or x to the power of 1 over 2, we know f prime of x will simply be 1 over 2x to the power of 1 over 2 minus 1, which will be 1 over 2x under the square root. So if we're plugging in 9 into our derivative, we get 1 over 2 times 3, which is 1 over 6. So let's put that here, plus 1 over 6 multiplied by delta x. Delta x again is going to be a subtracted from x. 9.1 minus 9 would give us 0.1 for delta x. Just like we did in linearization. We're left with just numbers, and now we're on to simple arithmetic. So 3 plus 0.1 over 6, if we're going to add that, we get 18.1 over 6. Now we have to find an exact value in terms of decimals, so we take the numerator inside the house. 18.1 divided by 6. 6 goes into 1, 0 times. 6 goes into 18 thrice. And the remainder will be 0. Put the decimal where it belongs. Get the next number down. 6 goes into 1, never. So we've got the 1 remaining. We get a 0 down since we're after decimals. 6 goes into 10 once. Subtract it from 6. Remainder becomes 4. Get another 0 down. 6 goes into 40 6 times, which will give us 36. We get another 4. Now if you notice something, we are headed for a dead end, a continuity of 6. So we'll have 3.016 recurring. So the approximate value of the square root of 9.1 is 3.016 recurring. That is through differentials. One final example that's a little more complicated than the first two examples. Let f of x is equal to the square root of x plus 3 approximate the square root of 3.98. Now many of you will be tempted to first set your a as 4. It is pretty close to 3.98, and you know an exact value of the square root of 4. However, our function is not just the square root of x. It is the square root of x plus 3. So we need a to be a number such that when it's plugged into this, we get 3.98. The only suitable answer really is let a equal to 0.98. So let a equal 0.98. Now if we get our differentials equation down, f prime at a delta x, we see that we are headed for f at 0.98 plus delta x, which in this case is already given as 3, is equal to f at a, f at 0.98. However, now we've headed into a problem. We do not know what f at 0.98 is. So what we're allowed to do in such a case is use this value right here of a to solve the entire question. I'll show you exactly what I'm meaning here. F at 0.98 is the same as saying f at 1 plus negative 0.02. We do know the exact value of f at 1, so we can use this as this, and then the right side of the equation will come correspondingly. So this will further become f at 1 plus f prime at 1 multiplied by delta x, which is the second part of our initial equation, 0.02. Of course, not to forget the negative sign. And this right here will be our differential equation. So f at 1, we know exactly what that is. 1 plus 3 is 4, square root of 4 is 2, plus f prime at 1. So we need to find the derivative of that, which I've already calculated as 1 over 2 square root of x plus 3. I know that f prime of 1 will be 1 over 2 times 2, which is 1 over 4, multiplied by 0.02. Negative, of course. And now we have 2 plus 0.02 over 4, which will become 8 over 4 minus 0.02 over 4, so 7.98 divided by 4. And now simple division again, so 7.98 inside the house. 4 divides into 7 once only. We get a remainder of 3, put the decimal up, get the next number down. 4 goes into 39 9 times. 36, subtract that, we get 3. 4 goes into 38 again, 9 times. We get a remainder of 2, running out of room there. Carry a 0 down. 4 goes into 20 5 times, and we get a remainder of 0. So the approximation of the square root of 3.98 is equal to 1.995 through differentials.